Okay, rotational motion part 4. So we're looking at this. We're saying, okay, we have 2 pi r's our circumference. We could lay this circle out. But the easiest way to do this is to convert this to radians and then to degrees, okay? Because we could use those skills here, okay? So basically what we're seeing is we have 4.8 radians, right? Radians per second squared. I can multiply by 180 degrees over pi, right, to get 275. This is a different way of solving this, but it really works, trust me. This is degrees. I like to look at it this way. You could also just do radians. You could do 4.8 radians over 2 radians per revolution to get the same exact thing to find a number of revolutions. But I like to use it during degrees because it's more visual to me to look at a circle and say, oh, okay, sorry, that's a really bad circle, but this is 360 degrees, that's 120 degrees, right? This is 270 and so on and so forth. So actually 275 is where we're going to lie, right? So we're like right about here. So it's like almost 300, it's almost like 3/4 of a rotation, right? But if I put this over 360, guess what that gives me? 0.76 revolutions per second squared, right? Therefore, I could say that 2 pi times 0.38 using my circumference formula equals 2.4 meters times 0.76, right? Revolutions per second squared, okay? From that, I'm going to get, it's 1.81 meters per second squared, right? Times 9.2 now is times my time equals my change in velocity, right? Because I'm doing it times my time now. So I have my acceleration times my time. So this is my delta V equals my acceleration times my time. It's written on the AP Physics 1 formula sheet. If I rearrange it so that V minus V initial equals the acceleration times the time, it's the same thing as writing delta V, right? Minus V initial equals my acceleration times my time, right? So when I solve for my delta V, I'm going to wind up getting my change in velocity is equal to 16.32 meters per second, okay? Now what I'm going to do is I'm going to plug that into another formula, believe it or not. I'm going to plug that into my change in my velocity squared, right, is equal to 2 times the acceleration times my change in my position, my delta x, okay? So basically what I do here is I plug in 16.32, this is from rest I believe, so yes, equals 2 times my acceleration of 1.81 meters per second squared, right, times my change in x. Therefore I get my change in my x to be 77.7 meters, right, which is the correct answer. And I also get, now what I'm going to do is I'm going to get my revolutions to be equal to delta x, which is equal to 77.7 over 2.4. The reason why I'm putting it over 2.4 is that because that is my that's 2 pi r, that's my circumference, okay? I put that over my circumference, that's basically visualizing, that's my distance around my circle. So when I take 77 as my distance that I'm traveling in that acceleration in that period of time over the distance of my wheel, or the circumference of my wheel, I'm going to get 32 revolutions, right? That's how many times I go around, and that's the correct answer as well for revolutions. So linear displacement 77 and the revolutions is 32. But the reason why, again, is because what's happening is I'm going around in a circle, right? I'm taking this circular path, right? So what's happening here is that I'm seeing, once I'm going around this circle, I have a circumference of 2.4, 2 pi r, right, to get 2.4. And then I'm traveling, I'm doing 77.7 meters in that velocity, which was accelerating over a period of time. My distance traveled total was 77.7. So when I divide 77.7 over the distance of my wheel, right, I'm actually going to do 32 revolutions. Okay, so basically that's how we solve this. It's another way of solving for a longer kinematics. You can use kinematics in these problems. There's plenty of ways you could solve using angular velocity. I like to use it visualizing a circle as a straight line and using kinematics. I think it's a good way of doing it. So in summary, I would use kinematics. I think it's the easiest way to look at this. Just look at a piece of rope or string, and then unwinding it will get you your full length of the string. That distance traveled over a period of time is really what's getting you, which is really what you're solving for with these values. And you can use your kinematics equations, which are very simple and are on your formula sheet, because unfortunately AP Physics, for some reason, the Physics 1 did not put that on the formula sheet. they didn't put, see, I put extra notes here, but they didn't put anything with, they didn't put anything for, momentum was the last unit, and they didn't put anything for this. I had to add my own little notes in here, but obviously for the test, you're not going to have these notes. You have to add these notes in yourself. Obviously, you'd have to memorize them, those formulas, or you could just use these kinematics equations like we just used that they give to us to solve for, circumference, revolutions, change in displacement, and velocity, as well as angular acceleration. So the angular accelerations, though, shouldn't be that terrible. You should be able to remember, that your change in angular acceleration is equal to velocity over the radius. Therefore, your angular acceleration is equal to your change in angular velocity over your time, right? Just knowing that distance over time is speed, and comparing that to your angular velocity over your time is angular acceleration. So that comparison really goes well there. So I apologize for the fact that these videos got split up. I really hope they helped you in some sort of way. If there's any other problems or concerns, please leave a link or a comment below in the bio. Thank you so much for watching. It is well appreciated. Take care and have a nice day.